Circuit diagrams. Drawing realistic pictures of circuits can be very difficult. Right? Here's what a resistor really looks like here. Here's a battery. Here's various wires. So we have symbols. This is the symbol for a resistor. This is a battery. And the longer line represents the positive terminal. The shorter vertical line is the negative terminal. And many people will write a couple iterations of that, okay? That's also good. That also represents a battery. And then this is going to be a wire. Also note that the circuit diagrams don't show where each part is physically located. It's just a picture of how they're hooked up to each other. Please draw a simple circuit that has a 9-volt battery and a 3-ohm resistor. What is the magnitude and direction of the current? Try it out here, and when you're ready, go to the next slide. Hopefully you got a picture that looks like this. We put the battery down here. We could put it anywhere in the circuit because this doesn't show physically where it is. We're just doing a schematic. And since the positive end of the terminal points in this direction, the conventional current flows like that. Here's our resistor up here. And to find the current, we use Ohm's law. So we have 9 volts over 3 ohms, 3 amps. Let's add a second resistor to this circuit. There are 2 ways to do it. One is series, and the other is parallel. In a series circuit, all charges must move through both resistors to get back to the negative terminal. So as the charges go this way, the only way to get back home is to go through both resistors. In parallel, the charges have a choice. Well, they don't really. They go where they're told by the voltage and resistance, but they can go either way. They can either go through the top or the bottom, not both, only one path. All the charges join up here again, and they go back to the negative terminal of the battery. Please examine these 2 pictures and let me know which resistors are in series, which are in parallel. So take a couple minutes, and once you're ready to look at the answer, move on to the next slide. The way to do this is to start at the positive terminal of the battery. You could go at the other side, but we'll just pick one, and go around the circuit. Take the shortest route there. You're not allowed to go backwards. You have to keep going forwards. And if you find resistors on the same route, if the charges don't have a choice, well, then you're in series. If there is a choice, is there a fork in the road, you're in parallel. So let's look at the easy one first, series. You leave the battery, you go through R1, and the only way to get back to the battery, to the negative terminal, is to go through R2, so that's in series. For the configuration over here on the left side, you leave the battery, and right away there's a fork. The charges can either go this way or this way, and then they'll all come back together again down here and get to the negative end of the battery, the negative terminal. So that is in parallel. Notice when we first showed parallel, we actually put them in what you know is parallel, right? 2 lines next to each other going in the same direction. They don't have to be that way. They just have to meet the test of if there's a different way to go to get back to the negative terminal, then your resistors are in parallel. So they don't have to be geometrically in parallel. Resistors and voltage from batteries, another name for that of course is EMF for voltage, determine the current. Circuits can be drawn as if there were only a single resistor and battery. By reducing the circuit this way, the circuit becomes easier to study. So what we're talking about is taking these 2 real resistors and replacing them with one virtual resistor that acts the same as the 2 of them. Another name for that virtual resistor is equivalent resistance, or R sub EQ. Let's start with series circuits. What happens to the current in the circuit to the right? Think about it and then move on to the next slide. The current passing through all parts of a series circuit is the same. So we have the current I coming out of the battery, and notice how all of it goes through both resistors. A handy thing to get into a good habit here is to put, let's see, the current label over where it's going through. So we have I1 going through R1 and I2 going through R2. And then we have I coming out of the battery. And they're all equal to each other. What happens to the voltage as it moves around the circuit? And that's the energy per charge as the charges move out of the battery and through the resistors. What happens to that energy per charge or voltage? The sum of the voltage drops across each of the resistors equals the voltage of the battery. So if the battery is supplying V, let's talk about V as energy, right? Because it's energy per charge. So let's just pick one little charge here. We'll call the charge Q. Charge has a certain amount of energy, okay? Certain amount of energy per charge or voltage. Goes through the first resistor. Some of that energy is transferred into heat and maybe light and other sorts of energies. So the charge now has less energy. You can consider it to be at a lower voltage level. Goes to the next resistor. It loses some more energy. Again, loss is a bad word. It transfers the energy to the resistor. Then at the bottom, it has used up all of its voltage, because the voltage over here, it's just by definition would be 0, and on this side it would be some value V. So the charges get back here. They're being pushed by the charges behind them, and they've transferred all the energy that they picked up from the battery to the two resistors. So you just add the two of them together, right? They transferred some energy here, transferred some here, and that equals the total amount of energy they were given by the battery. So V is equal to V1 plus V2. And when you're analyzing the circuit, you would put a V1 over there and a V2 there just to keep track of it. We'll do a little bit of math now. And we said on the previous slide that the sum of the voltage drops through all the circuit elements, in this case they're just resistors, has to equal the total voltage. Now what we're going to do is substitute in for each voltage IR from Ohm's law. So we have IR here, that's the total voltage. Then I1R1, that's going to be voltage across resistor 1. Here's resistor 2, here's resistor 3. Now this will work for any number of resistors. We're just going to cut it off at 3 here, just to make the point. What can we do between here and here? Well, we know that the current is the same everywhere. So if it's the same, we don't need the subscripts, just call everybody I. That's what we have here. Can you see the next step? You're right, divide by I, and we get R equivalent is just adding all the resistors. Summarizing, to find the equivalent resistors of a series circuit, add the resistance of all the resistors. If you add more resistors, what will happen to your equivalent resistance? Well, it'll just make it go up because you're adding some more positive numbers.